Let's start this after break session, the one before the lunch, and I'm very happy to introduce Professor Matheus Grasselli from the Math and Stats Department at McMaster University. He's going to talk about agent-based modeling today. So, please.
Thank you very much. So here you have the full title of my talk. In the program, I think there was an exercise in dimension reduction there with, to the least informative part of the title, it only had net innovation and agent-based model, so you don't know what it was applied to. But it's not as bad as what they did to Mark. Mark says intermediation complexity ... So we still don't know what he's going to be talking about. So this is a bittersweet story for the paper. I don't work on banking networks. The real expert was my late colleague Tom Hurd, who wrote a book on this subject and many papers. And he passed away untimely 2 years ago. And then his PhD student, Hassan Chehaitli, needed a supervisor. I was in the supervisory committee, so I became the supervisor, and then it took us, so he was about to finish at the time, but it took me some time to understand what he was doing and some more time to complete the thesis. So now the thesis is finished, and we, together with Wei-Ji Peng, who was a postdoc of ours at the time, we wrote this paper. I'm very happy it's coming out in a special issue of the International Journal of Theoretical and Applied Finance in honor of Tom Hurd, who was an editor of the journal. There are many other interesting papers in the special issue, one by Dilip Madan, one by Paul Glasserman, so many dear friends of Tom. And we were fortunate to include this paper there, which, unless some other co-authors come up with something that was in the work at the time, I think is going to be Tom's last published paper. So I don't have too much time, so I'll jump in straight to what the problem is. So if you don't know about Repo, repurchase agreements, I'm just going to set up the notation and the motivation here. So it's a type of lending that is structured as a sale. So you have something, and then you say, buy it from me. So when you buy, you give me money, but with the agreement that I'm going to buy back from you. So there's a period for the transaction. There is the market value of the thing that I will pretend sell to you, that is the collateral. I'm not going to get all the market value of the collateral. I'm going to get a bit less than that. I'm going to get the collateral times some haircut. So if say, I have an asset worth $100, I pretend sell it to you and I get $98 for it. And then I need to pay it back at some point. Typically overnight, but it could be a bit longer. I need to pay back not the 98 that I got, but maybe 99 because there's some interest, and that's the repo rate. There was some discussion yesterday about balance sheets and accounting. The accounting for this is slightly complicated. So if I'm borrowing, now what I have is I got more cash. So I got the cash coming into my balance sheet, but so it comes as an asset, and it's now recorded as part of my liquid assets, but I need to pay back, so it gets recorded as a liability. So it's a repo loan that I need to pay back. The lender, what they do is now they don't have that cash anymore, so they need to do an asset substitution. So instead of the cash, what they record, you would think the obvious thing is the collateral. No, it's not. What they record is my promise to pay back. So it's the reverse repo. So the repo is recorded as a liability for me. The fact that you're going to be receiving the money back at some point is a reverse repo. It's like the loan that you made to me. But what about the collateral? So the collateral, funnily enough, in the pretend sale agreement, now you were the owner. So I sold it to you, but it stays in my balance sheet. It stays in my balance sheet as collateral that is still mine because I'm going to buy it back, right? So you are the legal owner of the collateral, but not for accounting purposes, it's not part of your assets. It gets a bit worse because now what you can do, but you do have an asset. The asset is the reverse repo. You can use that reverse repo as collateral for something else. On the basis that you have that collateral that you're going to potentially use if I don't pay you the loan back. So this is called rehypothecation. So you can use the reverse repo that is part of your assets now in order to borrow cash from yet another counterparty. So this is the setup. If it's just a simple repo, the lender posts collateral, the borrower sends cash. The collateral stays in a segregated account, not in the balance sheet of the lender. If it's a rehypothecated repo, then the transaction can continue and can potentially continue for many more steps. So this creates problems. So we want a model to connect these banks and then see what happens dynamically as the value of all those assets change. So the model is an extension of the Guy-Haldane-Kapadia model, which then has this kind of structure for the balance sheet of each individual bank. So here you have assets and liabilities. On the assets, so it looks a bit complicated, but we'll simplify later. So you have uncollateralized loans. So these are just interbank borrowing. So uncollateralized loans that are made to other banks they're called A. So this is actually the sum of all that is made. And if you think of a matrix, it's the row sum, because now, so for the row for bank I, there's going to be all the loans that were made to all of the other banks, 1 to n. Then there's the collateralized loans, the reverse repos. This is the collateral asset that is used for the transaction. These are all the liquid assets, so these transfers of cash that we mentioned. And these, importantly, are fixed assets, so they're illiquid. So think of them as a mortgage portfolio or something that the bank has. On the liability side, you have the opposite, the things that you borrow from other banks uncollateralized, the things that you borrow on the repo market, deposits that were made by external agents, so like clients of the bank, and then the remainder is the equity. So the network is going to look like the interbank network, where each of the nodes has that balance sheet structure that I mentioned, and then there are external agents. There are the providers of the fixed assets and the providers of the deposit, and also there's going to be a central bank that is going to come here and lend to the liquid assets part of the bank. And so these are going to be the nodes. The edges are going to be the non-zero entries in this either collateralized or uncollateralized lending. And here, to go back to Santos' talk yesterday, importantly, there's going to be one edge if there's an uncollateralized relationship with a certain weight, and a different edge for a collateralized lending with a different weight. And quite obviously, if you do that trick of saying, if you have a weight of 10, it's the same as 10 links of weight 1, that doesn't work here, because they're very different meaning for the two different edges. One is collateralized, the other is uncollateralized. So in the Guy-Haldane-Kapadia model, the crux of it is what happens if some bank is facing a liquidity constraint. So they come up with this inequality here that needs to be satisfied by bank I. Don't worry about term by term, but basically it means that you need to have enough assets to liquidate if you need to pay out some of those liabilities that you have. So for example, you can interpret epsilon as a deposit shock. Somebody comes in and withdraws some money. This is some other bank that has uncollateralized loan that you made towards, and then they call it back and things like that. And these are the different conditions that occur if you want to pledge some collateral in order to obtain some money in order to pay the liabilities. So the point is, what happens if this is broken? So say this epsilon increases and this goes negative. So then they need to restore that condition, and then what they assume in the paper is that they do it by calling uncollateralized loans. So they're going to go and liquidate part of their AU, which is not in this equation, is their uncollateralized loans. They are going to call it in order to raise money. So what that does is that it propagates then the fact that the inequality is not satisfied to another bank, because it's going to increase that term for another bank, J. So now that bank is going to have to do that, and then potentially this is going to propagate through the network. And what they find is now under many different assumptions, but they find that this has a threshold behavior, because now if you imagine if you have many liability, many counterparties for your liability, then just calling some of those loans, the effect on each of them is going to be very small, so they're going to be able to absorb that shock. And if you have few counterparties, then potentially it's going to spread through all of them, and in a large way that then will spread to their counterparties as well, and then you have the shock spread to most of the network. So there's this threshold behavior with the average connectivity of the network. Okay, and I need to speed up. So what we're going to do in the paper is, because they only consider this recalling uncollateralized loans, but then they stop there and they say, we do that because, it's not reasonable to liquidate fixed assets because fixed assets are illiquid and they're going to reduce their value. It's also not reasonable to recall repos because that's going to make your collateral constraint bad, because remember, you use your own reverse repos as collateral for something else. And then they stop the paper. And so what they find is that these banks are going to hoard all liquidity that they can with their uncollateralized loans and just sit there. And the question you should be asking yourself is, okay, but what if that's not enough? They did all of their uncollateralized loans, but they still face liquidity constraints. So however unreasonable it is, they still have fixed assets to liquidate, and they still have reverse repos to call. But they don't go there. It was an early paper. And so in a sense, the whole motivation for this project is how do you extend that when you now allow banks to liquidate fixed assets and recall reverse repos. But then you get to this problem. Now, what happens if the asset price goes down? So we need to put explicitly a price impact, which will affect banks now, even if they were not connected to anything, because this is a common asset, so it's going to reduce their equity. They could go and be insolvent because of that. And if you recall reverse repos, that is going to change the entire collateral dynamics for the entire network. So our point is to investigate exactly those two features. So we break out the one constraint that they have in the paper into three constraints. There's separate constraints that need to be satisfied: a collateral constraint for the repo market, a liquidity constraint that basically means that you have enough liquid assets, so your cash buffer is greater than zero, and a solvency constraint that says that your equity is greater than zero. And then now it goes into the nitty-gritty of the model. Now every day there needs to be some mechanism that reconciles all these things. So this is the end, going from day k to day k plus 1, an epsilon before the end of the day where markets really operate. There's going to be a market operator that checks those constraints. And if the constraints are not satisfied, then the banks can do two things. First, they're going to go into an asset substitution. They're going to try to sell some of their assets and restore the constraints. And we're going to see in a second how they do that. But then even after doing that selling of assets, they cannot satisfy the constraint, they need to be removed. So there's an auction part and there's a resolution part. What does the auction part consist of? Well, we break that in two steps because not everything is equal here. So collateral is more liquid than fixed assets. So if you still have excess collateral, you're going to try to satisfy whatever constraint that you have by selling as much collateral that you can. But if you have a lack of collateral, then you want to satisfy that first because that's important for the well-functioning of the repo market. So you're going to try to sell fixed assets to restore that. That's the first sub-step. If you cannot satisfy your collateral constraint after doing that, you're out. Then the banks that survive move to a liquidity sub-step when they try to restore the liquidity constraint with the only thing that they have left, which are the fixed assets and the reverse repos. And now it's a behavioral choice because you can get killed in either side and it can have consequences for the network in either side. So do you do fixed assets first or reverse repos first? So we have to assume that there's a distribution of preferences among the banks, and then we see what the distribution of preference generates. The resolution is also interesting because we first impose, and you'll see why next, we first impose that there are no cycles in the set that needs to be resolved. So we declare now that there are some banks that need to be taken out of the network. We need to remove the cycles, and you see why in the novation step. And then removing cycles is not a unique operation. There are different ways of removing cycles, but you need to choose like which order to do. Could be a lexicographic order, could be whatever you want, but that might impact the end result. And we'll see, no, not in this talk, but in Hassan's thesis, there's some investigation on what is the effect. The hint here is that the novation steps minimizes the impact of the arbitrariness of netting. But then what is novation? Novation is when you now have a bank to be removed, the bank might be a net lender or a net borrower, so you rewire whatever the excess part is into the remaining bank. So let's just walk through this example. The other one I'll leave on the slides. But this is a bank that is net borrowing. So it means that it owes $60 in total, and it's going to receive $45. So it's net borrowing. So the point here is that it's going to receive this 15, but it shouldn't have any claims on that 15 because it owes more than that. So that 15 that Bank 2 owes to Bank 5 gets redistributed to the two banks that Bank 5 owes to. So it gets redistributed to 1 and 4 in proportion to their liabilities. So 1/3 goes to 1 and 2/3 go to 4. So 1/3 is 5, goes to 1, and 10 goes to 4. And then the same thing for Bank 3. 1/3 goes to 1, so 10 goes to 1, and 20 goes to 4. Now, what you should notice is that the assets and liabilities of all of the other banks are completely unchanged by that, and also that this remaining bank now is a pure borrower. Because it's a pure borrower, you can just go and sever the links in the closeout without any ambiguity. Of course, some of the banks are going to take a loss, but you know exactly which banks are going to take the loss. There's no ambiguity of what is affected in the network. For a net lending bank, it's the opposite thing, and you can follow the calculation. Now, this is just an example for one bank, but we define mathematically what novation is, and we prove then properties of novation. So what I just said, that after you novate, it becomes either pure borrower, pure lender is generic. Also that the liabilities and assets of the other banks remain unchanged is generic. But importantly, if there is no cycle between the two banks that are being, say you have two banks to novate and there's no cycle between them, then the order in which you novate the two doesn't make a difference for the resultant balance sheet of everyone else. And also importantly, novating one bank doesn't introduce cycles in the network. Put that together, you have the result that if you have a resolution set that is acyclic to begin with, then you can do novation of any arbitrary set of banks in that subset, one at a time, in any order that you want, and the result balance sheet of all the banks are going to be the same. So this is the analytic part of the paper that involves a lot of tedious linear algebra and careful calculations, and you arrive at that result. Now, I'm just going to my simulations. So in each of the simulations, we have a way to populate the balance sheets that follows Guy-Capadia, 250 banks. We make them have some amount of equity in there. There is reasonable, some liquid assets, and so on. And then we're going to be doing some shocks in there. I promise I'll take no more than 1 or 2 minutes. In each of them, we're going to be recording those metrics. So systemic hoarding frequency is what proportion of the simulations you see more than 10% of the banks having to recall reverse repos. Then the extent of it is conditioned on that happening, how many of the banks actually did it. And then the same thing for default. What proportion of the simulations has more than 10% of the banks defaulting, and conditioned on that happening, what proportion of the network defaulted. Just the Guy-Capaldi result had that it's only for hoarding and for the uncollateralized loans, and this is the threshold behavior that I mentioned. For low connectivity, you see some systemic hoarding and propagation to the entire network, but then as soon as the connectivity is high enough, you don't see anything, and then there are different configurations of the network that make that threshold larger or smaller. So in our setting, and now I got to really flash, and it's good that you can't see because there's no time. But what we do is calculate those four metrics under 3 different scenarios of what proportion of the banks does reverse repos and fixed assets. And what you can't see, because now it's going to be too fast and too mysterious, but it's like, as long as there is any degree of illiquidity in the fixed asset and the shock is high enough, calling reverse repos make no difference because default dominates. Default happens very fast and happens for the entire network. If there is no illiquidity in the fixed asset, then there is no default, and there is not too much hoarding either. So in order to see some non-trivial interplay between systemic hoarding and systemic default, you need to adjust these 2 parameters. So we do a little bit of experimentation, fixing one, varying the other, fixing the other, varying the one, and we find kind of a sweet spot between the size of the shock and the size of the liquidity parameter that then reproduces our first experiment with some non-trivial behavior. The non-trivial, what I mean is that it's not all default and no hoarding, or no default and no hoarding. There's some amount of hoarding and some amount of default that you can now try to analyze depending on the connectivity. And now I end, and the conclusions are there, but I won't repeat them. Thank you.